Now that we're building a picture of what the electronic structure of an atom looks like, we need to build in some conventions to track electrons. And this is something I consider like the bookkeeping part of electronic structure. It doesn't necessarily represent something extremely accurate, but it does present it in a way that is easy for us to understand and make predictions off of. Even though it is founded in the solutions to the Schrodinger's wave equation. Um, so let's talk about quantum numbers and electron configurations and orbital diagrams. To define an electron configuration, I'm going to focus on our simplest version of an atom, the hydrogen atom. So an electron configuration is going to describe the orbitals that are occupied with electrons, and it becomes this address for the electron within the atom. What orbital is it in? What shape? What spin it has? So here's the hydrogen's electron configuration. And if I was going to write it, the thing I would write would be 1s and then a superscript 1. And what this represents is the 1 in front of the s represents the energy level. And so that's the n quantum number. The s is the type of orbital, which is the L quantum number. And if it was 2, then it would be P. And if it was 3, it would be D. And 4 would be F. And then the superscript is always going to represent the number of electrons that are actually in that orbital. And for hydrogen, it just has 1 electron. So it's going to only have 1 in that superscript rather than 2. So this electron configuration gives us information about the quantum numbers that these electrons have associated with them. And those, remember, come from solving the Schrödinger wave equation. And so this n equals 1, L equals 0 that we are determining are part of the solutions to the Schrödinger's wave equation. It shows that the electron in the hydrogen occupies the lowest possible energy orbital at n equals 1. So then when we start thinking about multi-electron atoms, things become more complicated. And the Schrödinger wave equation now gets so large and complicated that it cannot be solved exactly. But we can approximate solutions. And when we approximate solutions, it shows that orbitals to have hydrogen-like behavior, as in electrons will occupy that lowest possible position and it'll follow the pattern set out by that hydrogen solution that we were able to do exactly. So to be able to look at these multi-electron atoms, we need to add in some concepts. And we've already talked about one of them, which is the electron spin. That is the spin quantum number, that each orbital will be able to contain 2 electrons, 1 spin up, 1 spin down. And we also need to talk about the degeneracy of the energy sublevels. So degeneracy means the same. And our sublevels of energy, so the different levels of ways, orbitals that electrons can occupy within an energy level n, are not actually going to be the same, which means they're not going to be at the same energy. An s and a p orbital will not have the same energy. So let's get into this. So reminder, here are our quantum numbers. There are abbreviations and a description of what they are. And so our principal quantum number n is our energy level. Our angular momentum L is our orbital type, SPD. Our magnetic quantum number is m sub L, and that's the orientation in space, where it lines up on the XYZ plane. And our spin quantum number is m sub S, that's the magnetic spins of electrons. And the Pauli exclusion principle states that no 2 electrons in the same atom can have the same 4 numbers. So there are 2 electrons in every atom that can have the first 3 numbers be the same, but then they'll differ on their spin number. And so that means that this Pauli exclusion principle means that we can't have more than 2 electrons per orbital. And when they both occupy the same orbital, they have to have opposite spins. And we call this spin pairing. So when two electrons have opposite spins, they are kind of, there is a connection between, it's not a connection. If one of their spins changes, the other will too instantaneously. And so that's what we think of as spin pairing. And so looking at this quantum number, m sub s again, going into a bit more detail, we're seeing that atoms can be, in general, separated into two groups if you apply a magnetic field. And it'll show that electrons will generate a magnetic field as they spin around their axis. So the electrons themselves, these little tiny things, are spinning. And one will spin, will have a net magnetic field pointing north when it spins, and the other will have a net magnetic field pointing south when it spins. And this is where we get the idea of spin up and spin down. So if that magnetic field points north, then we're going to have a spin up electron. And if it points south, we're going to have a spin down electron, or positive 1/2 for spin up and negative 1/2 for spin down. And we only use negative 1/2 and positive 1/2 for our m sub s numbers by convention. This is not a value that is part of a Schrodinger wave solution. So it doesn't come from the Schrodinger wave equation, rather from our observations of behavior of electrons in a magnetic field. What we typically use is half arrows, and I have full arrows here for some reason, but typically you'll see one electron represented by a half arrow like this, or spin down like that. So if I was going to show that in an orbital I had two electrons that were spin paired, I would do one half arrow up and one half arrow down. So now we can start building electron configurations beyond that hydrogen atom. And let's look at helium, which would be a multi-electron atom, but still very simple. It only has 2 electrons in it. So those 2 electrons are still going to occupy the lowest possible energy level, which means it's going to be at the N energy level of 1. It also is going to then pair those 2 electrons in the lowest possible shape or energy shape, which is S, right? And if you're in the N equals 1 energy level, you only have one option for an orbital shape, and it's S, because that L equals 0. There's no other options. So that's our L equals 0. And that 2 in the superscript is our number of electrons. And helium has 2, so it has 2 electrons. So the way I would write this for helium is I would have a 1s orbital, and you could do it as a box. I always just do it as a line, and then I would have 1 electron. And for my helium, I would have 2 electrons with opposite spins indicated by the opposite directions of the arrows.